Everybody, welcome back to another video. Now, I regret to inform you, I have been lying to you all this time. No, not on anything important, it's just the glasses. Yes, I am as weak and feeble-eyed as many of the population, and I'm sorry for having deceived you this whole time. Alright, in this lesson, we're going to be talking about higher order derivatives. And some of you might have been thinking through the course of this class, well, if the derivative is so great, where's derivative 2? Well, here we go. Higher order derivatives are what happen when we take a derivative of a derivative, or derivative of a derivative of a derivative, and so on and so forth. So, definition, the second derivative of a function f is the derivative of its derivative. Which we're going to use the limit definition for, and we're going to say f double prime, so 2 tick marks instead of 1, of x is the limit as h goes to 0 of, so with the original limit definition for the first derivative, it was f of x plus h minus f of x over h, but now we're taking the derivative of a derivative. So we're going to be working with f prime of x plus h minus f prime of x divided by h. So that's our limit definition for the second derivative. You can construct the third derivative, fourth derivative, however many derivatives you want, similarly by just repeating this process, increasing the amount of derivatives you're taking there each time. So we have some notation for higher order derivatives. We have f prime of x is the first derivative. This is the one we've been working with all the time. F double prime of x is the second derivative. F triple prime of x would be the third derivative. Then when we get to 4, we break the pattern because nobody likes writing 12 billion tally marks, and we write f parenthesis 4 of x. And for 5, we would write f parenthesis 5 of x. It is important to put the parentheses around because otherwise you're talking about, hey, I'm multiplying the function by itself 4 times, but we don't want to be doing that. We want to be taking 4 derivatives. So on and so forth. Other notation, we have that denotation, which I've never used in this course and really, frankly, haven't used in any of my personal mathematics, but I'm still required to write it down. Or I guess I'm not, but I obligate myself. So we have derivative of f of x, second derivative of f of x, third derivative of f of x, and so on and so forth. Technically, the derivative is what's known as a linear operator, and that's how you get this pattern. So squaring and cubing is actually an appropriate thing there. But that's besides the point. That's another course's work. If we write y is equal to f of x, we have, so we know dy dx is the first derivative of the function. The second derivative, the notation gets a little strange. So we're going to put d2y, so like a superscript on the 2 and exponent on the d. But then on the bottom, we're going to put dx squared. So in between on the top, to the right on the bottom. Is that a little confusing? Yes, it wasn't my idea. blame Newton. Or, no, this is Leibniz's notation, so blame him. Okay, so on and so forth. So we have d3 of x over dx to the fourth, yada, yada, yada. You can also use the same kind of prime notation as this. So you can talk about y prime, y double prime, y triple prime. And then you also do the parentheses for any derivative of order 4 or higher. Alright, so these are all of our forms of notation for higher order derivatives. And the great thing about higher order derivatives is we don't really need to do that much more work to develop, okay, how do you find a higher order derivative? Since we've already mastered taking derivatives, and finding a higher order derivative is just taking derivatives of derivatives. Derivatives are just another function. So all the work that we've done so far can contribute to an easy understanding of this, which is nice. Let's do some examples, just to make sure that everything is squared away well in our heads. Alright. Let's find all derivatives. What this says is it means find the derivative of every order. So the first derivative, the second derivative, third derivative, fourth derivative, fifth, sixth, seventh, 12th, 27 billion and fourth. You might be like, isn't that a lot of stuff to write down? Yes, it is, but don't worry, we're going to do a simpler example. So find all derivatives of f of x equal to 24 x to the fourth minus 6x cubed plus 2x squared minus x plus 1. Alright. Okay, well, technically, this is our 0th order derivative, right? Taking no derivatives at all, just f of x. Let's start down the chain. F prime of x is equal to d dx of fx, which this one I'll do full out, and then the other ones I will do without the steps. d dx of fx. So d dx of 24 x to the fourth minus 6x cubed plus 2x squared minus x plus 1, which, applying the sum rule and scalar multiples rule, is 24 d dx of x to the sixth minus 6 d dx x cubed plus 2 d dx x squared minus d dx x plus d dx of 1. And now, applying the power rule and the constant rule, technically, we get, let's see here, 24 times 6 is 120 plus 24, 144. X to the fifth minus, why did I write down 6 here? That should have been a 4. That's not even a math error, that's just a me writing down things wrong here. Whoops. Okay, so we're only doing 24 times 4. We're going to have 80, 96 x cubed minus 18 x squared plus 4x minus 1. So 96x cubed from here, 18x squared from here, and 4x from here, and finally our minus 1 from there. So that's our first derivative, f prime of x. so now to find the second derivative, we just take the derivative of that. So d dx of f prime of x, which is equal to, go through the exact same process of applying these rules, and you get, let's see here, 270 plus 18, 288. Yes. X squared minus 36x plus 4. Alright, so that's our second derivative. Our third derivative is just the derivative of the second derivative. I suppose I should put a box around that. And that's equal to, okay, 2 times 288 is 400, 560, 576. X minus 36. Alright? And now we're getting really close. It's getting easier and easier as we go. Fourth derivative of f(x) is d dx of the third derivative, which is just going to be equal to 576. Okay, and now we're nearly done. Let's notice now that the nth derivative of f of x is equal to 0 for n greater than or equal to 5. Right? Why is that? Because once we take the derivative of the fourth derivative to get the fifth derivative, we'd have 0, a constant, right? Because we're taking the derivative of a constant and we get another constant back. And you keep taking the derivative of 0 over and over again, right? And it'll just keep spitting out 0. So the nth derivative is 0 for all n greater than or equal to 5, which is why finding all derivatives is a doable problem. You don't actually have to write out infinitely many things. This takes care of all the remaining cases. Suppose I should box that for the fourth derivative. Alright, so that's a good example. Let's do another. Some of you might be asking yourself, okay, well if I can take higher order derivatives, is there such a thing as negative derivatives? The answer is kind of. We'll learn a bit about what the quote-unquote negative order derivatives are later in the course. And some of you more adventurous types might even ask, well, can I take like a half derivative or like a 12th derivative? Yes. But that's really complicated, in fact, and so complicated that I barely know how to do it. So we aren't doing this course. Okay. Simpler problem, one we can handle. Find the second derivative of y equal to x squared minus 1 to the 3 halves half. Alright, well to find the second derivative, we go by way of the first. So let's compute. dy dx is equal to, okay, let's use our chain rule. Well, you can write this on the lower line. Why use the chain rule? Because it looks like I have a clear composition inside, outside. So if we let u equal x to the 3 halves, then y is equal to, sorry, u is not x to the 3 halves, u is x squared minus 1. Then y is equal to u to the 3 halves. Variable choice, whatever. Anyways, y is u to the 3 halves, which means that dy dx equals dy du times du dx. Again, this is by the chain rule. dy du, easily computed with the power rule. 3 halves u to the 1 half. 3 halves minus 1 is 1/2. du dx is just 2x. Alright, so doing some simplification and back substituting in for u, we get that the first derivative is going to be 3x times the square root of x squared minus 1. Or in other words, 3x times x squared minus 1 to the 1/2 power. Alright, and now to find the second derivative, we're just going to take the derivative of this. Alright, we're going to keep the same substitution of u is equal to x squared minus 1, and we're going to start trying to take the derivative. The second derivative of y with respect to x is the derivative of the first derivative, aka dx of 3x times x squared minus 1 to the 1/2 power. Alright, so by the product rule, right, since we have two things getting multiplied here together, this is equal to first chunk times the derivative of the second chunk. Right? The kind of clear chunks here are the 3x and the x squared minus 1 to the 1/2 power. Plus second chunk times derivative of the first chunk. Okay, derivative of 3x is going to be easy, so we're going to just do that like a snap and worry about this part here for now. But thankfully, that part is handled for us by the chain rule. How? Well, we can again do this process here, and we'll get 3x times, okay, it'll be 1/2 times x squared minus 1 to the negative 1/2. 1, 2, 1, 2, yep. Times the derivative with respect to x of x squared minus 1. So this is more explicitly what we did over here, right? We're taking the derivative, the whole thing, multiplying by the derivative of the inside. That's the chain rule. Plus, of course, our second chunk, which is x squared minus 1 to the 1/2 times 3. So I'll just put the 3 in front. Alright, ddx of x squared minus 1, easy to compute. And we're going to be left with unsimplified 3x times 1/2 x squared minus 1 to the negative 1/2 times 2x plus 3 times x squared minus 1. Alright, let's simplify that a bit, clean it up. I'm going to erase this chunk over here. I'll leave this here and I'll rewrite the first derivative so we see where we came from. Alright, so we have y is equal to x squared minus 1 to the 3/2. dy dx ended up being 3x times x squared minus 1 to the 1/2 power. And now here, let's do some simplification. Second derivative is, okay, we're going to have 6x squared times 1/2, that's 3x squared, times x squared minus 1 to the negative 1/2, plus 3 times x squared minus 1. Okay, so we ask ourselves, is there any way to simplify this further? If you turned in this, I would not be upset. But we can actually do a little bit better. Let's factor out 3 x squared minus 1 to the negative 1/2 power times, we're going to be left with x, that's all that's left from that first chunk, plus x squared minus 1 to the 1 plus 1/2, just by our rules of exponents. So 1 plus 1/2 is 3 halves. Like that. Right? Why is that? Because if we distributed, it's easy to see that this first chunk gives us, this should be x squared. There we go. It's easy to see that this first chunk multiplied together gives us back this first term. And for the second term, 3, when we factor out an x squared minus 1 to the 1/2, if we multiply that back in, it'd be 3 halves plus negative 1/2, which would give us a positive 1. There's an imaginary exponent of 1 on that, so we're all good. Then we can rewrite that a little more elegantly, if we wanted to, as 3x squared plus 3 times x squared minus 1 to the 3 halves power divided by x squared minus 1 to the 1/2 power. It's kind of your personal opinion. Which one of these you think is more elegant, I will accept either. Alright, so this is our second derivative. That's exactly what we want. So we are done with this example. Alright, let's do one more example. You might ask yourself, why are higher order derivatives useful? Well, a lot of physical relationships between objects are actually modeled in terms of an object and its derivative. For instance, one of the primary applications of the first derivative comes from physics, where they're like, okay, if I have an object moving, then its speed, or rather its velocity, because derivative does have direction on it, plus or minus, its velocity is the derivative of how its position is changing. Okay, makes sense? Then the acceleration of an object is how its velocity is changing. So the acceleration is the derivative of velocity, which means acceleration is the second derivative of position. And then there's more derivatives after that with increasingly fancy names. But those don't matter for us, and they don't really matter for our course, so we aren't going to do an example with them for now. For now, what we're going to do is we're going to let f of x equal x cubed minus 2. And we want to find f of 1, f prime of 1, and f double prime of 1, and finally f triple prime of 1. Alright, well, to do those things, we should probably first figure out what f prime of x, f double prime of x, and f triple prime of x are. We already have f of x. Okay, well, f prime of x will be d dx of x cubed minus 2, 3x squared. F double prime of x will be 6x, and f triple prime of x will be 6. This is application of the power rule and the scalar multiple rule. Make sure you are tracking how this goes along. And feel free to ask me for examples when we meet together if you aren't tracking. Okay, now we can find all the information that we want. F of 1 is just plugging 1 into our function right here. So we get 1 cubed minus 2, that's 1 minus 2, negative 1. But f prime of 1 is 1 squared is 1 times 3, 3. F double prime of 1 is 6 times 1, which is 6. And f triple prime of 1 is also 6, because no matter what x is, this is a constant function, 6. So those are our answers, and we might ask yourself, okay, numerically, what do these really have to do with each other? And the answer is absolutely nothing. So you cannot, that's actually a good lesson, you cannot infer numerical values of the derivative from the previous derivatives. Always, always, always take the derivatives as functions first and then start plugging in your values. Alright, I think that's all for higher order derivatives for now. In chapter 4, which will be in a few weeks from now, we'll see kind of what these derivatives are useful for in terms of what information can you get about a function from its higher order derivatives. Alright, see you guys in the next video.